questions 21 through 25 on the 2004 grade 12 AMC 12B. The graph of this equation is an ellipse in the first quadrant of the xy plane. Let A and B be the maximum and minimum values of y over x over all points xy on the ellipse. What is the value of A plus B? So we have some ellipse. I don't know what it looks like, so I just drew it in blue there. And then they give you the equation of that ellipse, like that. And then they want you to figure out some very interesting things here. They're saying that A and B are the maximum and minimum values of y over x. So what does that mean? Y over x is equal to A, and that's the max. And then y over x is equal to B, and that is the minimum. So how do you interpret that? What do they mean by that? It's probably one of the more difficult aspects of the question, is just understanding what the question is saying. Well, this is what it means. You take a line, and that line is going through the origin, like that. And it's going to be tangent to the ellipse at one point. It's only going to touch the ellipse at one point, so approximately there. And then in a very similar way, you're going to have another line that goes through the origin, and it also touches the ellipse at just one point, so approximately right here. Now these two lines, because they go through the origin, they are both of the form y equals mx, right? Because 0, 0 is a point on the line. Now if I isolate for m, watch what happens. You get y over x is equal to m. Perfectly allowable. And that is what these two mean. This point right here represents A. Why? Because that is when y over x is at its maximum. And this point down here represents B. That is when y over x is at its minimum. So again, this line is also the form y equals some slope. Let's call it m2x this time. But if I isolate for m2, I'll get m2 is equal to y over x. And this, because it's minimum, represents my b. Okay? So that is the interpretation of the question. So I'll put that in there, b. And this guy up here, y over x, is equal to a. All right? So before I move forward with the question, just please take a moment to understand that. That's probably the challenge of the question. Now that you have understood it, let's move forward with our question. So we are given this big long formula here, and we are told we have to interpret and work with that. So let me write it all out. And then since these two lines that I drew are basically tangent to that ellipse, this point right here and that point are intersection points. So how do you find the intersection points? Well, you just substitute into here. So I'm going to substitute y is equal to mx into this equation right here. So wherever there is a y, I'm going to put mx like that. All right? So this becomes 3y squared, which is mx squared, minus 11x minus 20y, which is mx, plus 40. And then we simplify and collect terms, like terms. So this becomes x squared, and let's see what is x squared. Looks like I've got a 2 here. Put this in brackets. I've got a 3m squared from here. And anything else? Yeah, right here. I've got an m. So that takes care of my x squareds. And then I'll have some coefficient in front of x. And let's see, what is that? That's minus 11 minus 20m. and then I've got this lone 40 at the very end there. Okay? Now this is obviously a quadratic equation, and we have to use a quadratic formula to figure out the value of x. And the value of x, of course, will be in terms of m, unfortunately. It's not as pretty as we had hoped. But there's one very important thing, is that when we look at just the ellipse and this first line here, okay, so forget about this bottom line for a minute. Just look at this green line and the ellipse. Since they are tangent, there's only one point of intersection. All right? Now, when you want only one point of intersection, the quadratic equation, the discriminant must be 0. So let me write that out. So we want one solution to this equation, so we want the discriminant to be 0. If you remember in the quadratic formula, x is equal to minus b plus or minus the square root of b squared minus 4ac. You all remember that, of course, or all over 2a. The discriminant is, remember, it's this guy right here, b squared minus 4ac. Now, normally, that discriminant is some number, right? And therefore you get two solutions. You get minus b plus the discriminant all over 2ac and minus b minus the discriminant over 2ac. But if the discriminant is 0, then you just get one solution, which is minus b over 2a. And that's what we want. We want one solution, because just look at the line and the ellipse, right? Just forget about the bottom line right here. Just look at those two. We only want one solution, okay? So that's why we want the discriminant to be 0. So what we need to do is figure out what is the discriminant of that big long equation, and we set that equal to 0. Well, the discriminant is of the form b squared minus 4ac. So what is b squared minus 4ac in our big long equation up here? All right, let's see. b looks like minus 11 minus 20m all squared. Minus 4a is 2 plus 3m squared plus m. And c is just 40. Okay, so that is our discriminant. So when you simplify this, let's see what we get here. 121 plus 440m plus 400m squared minus 320 minus 480 m squared minus 160 m, and when you collect like terms and all that, you get minus 80 m squared plus 280 m minus 199. This is the discriminant, and we want basically this to be 0, and that's why I set it equal to 0. All right? So this guy here will give two solutions, and one of those solutions will end up giving us A, and the other one will give us B. So for example, when we solve this, one solution will result in this point, and that will be basically A, and the other solution to that discriminant being set to 0 will give us this point, which is our B. All right. Now the good news is we actually don't need to figure out each individual value. We can just use the sum, because the sum is what they want. They want us to find A plus B. If you remember in the question, they say, what is the value of A plus B? Now A plus B, it's a little bit easier. Why? Because in any kind of a polynomial of the form ax squared plus bx plus c, the sum of the roots is equal to, if you remember, minus b over a. So if you have two roots to this quadratic and you just want the sum, you just use the formula minus b over a. So the sum of the roots, therefore a plus b, is minus b over a in here. This is, of course, b, so it'd be minus 280 over a, which is minus 80. And therefore that is equal to, in lowest terms, 7 over 2. And that's basically the answer to this question. So in my opinion, it gets a little tricky simply because you have to interpret this first. And the interpretation, I think, is the hardest part. So it's a good question. Go back, review it, take out a piece of paper, do it on your own, and understand it, because this kind of question does come up again and again where you are using ellipse equations. So the answer was 7/2, so number 21 is C. This square is a multiplicative magic square. That is, the product of the numbers in each row, column, and diagonal is the same. If all the entries are positive integers, what is the sum of the possible values of G? So this question is one of those, let's, do the math. There's no, unfortunately, magic formula. It's just sort of a, plug away and let's see what we get. So the first thing is we're going to try to get all the entries in terms of one variable. So in a series of steps, we'll just keep plugging away and try to get everything in terms of one variable. The very first thing, of course, is I've got to make this a little bit bigger here because this is not going to be sufficient. It's too small. All right, so a little bit bigger, so let's begin. Here we go. So the first one, let's see here, concentrate on this one here. That's the one that has two numbers, right? Probably be a little bit more helpful than any others to begin with. So we got 50 times E times 2 has got to equal any other row, column, or diagonal. So you can begin anywhere. I'll just begin here, BEH, since that will allow me to get rid of an E, I think. So B times E times H, and therefore the E's cancel, left with 100 equals BH, and therefore H is equal to 100 over B. Okay, so H is 100 over B, so I'll stick that in there, 100 over B. And there's so many different ways of approaching this question. I'm just trying to do it in the simplest way I can. Next one, 50. I'm using the same diagonal there, again, that one. Let's use another one with E in it, CEG. How about this guy? That will allow me, once again, to get rid of the E. C times E times G. So 100 is equal to C times G, and therefore G is equal to 100 over C. All right, so put that in there. 100 over C like that. Okay, let's keep going here. Where do you want to go next? Number 3. Well, it's like that saying, if it ain't broke, don't fix it. Let's just keep going with that one. 50E times 2. That seems to be helping me. Let's get another one of these that involves E. This means 100 is equal to D times F, and therefore F is equal to 100 over D. I put that over there. 100 over D. And then next step, let's see. Let's start looking at something that involves the same letters, because I'm trying to get everything in terms of one, right? So I see here 50, B, and C, and then these guys have B's and C's in them, which is what I created. That should help me. 50 times B times C, and it's 100C, right, for this guy, and then this one is 100 over B, and I've got 2. Okay, so cross multiplying, I'm getting B squared times C squared, and then put all the numbers on one side. We get 200 times 2, so 400. And if you take the square, you get BC is equal to 20. And remember, these are all positive integers, so that's why there's no negatives. And then isolate for C, and you get 20 over B, like that. Okay, so I put that in here, 20 over B. Okay, so slowly we're trying to get everything in terms of one variable, and I think that one variable is most likely going to be a B. All right, now let's see, what else can I do that looks similar? I think column 1 and column 3. This guy, column 1 and column 3. That should help. So that basically gives me 50d and 100 over c is equal to 20. Well, instead of introducing yet another variable, let's just stick with the c, because I've got c on the other side, and then 100 over d, and then the 2. I think that will be a little bit better. All right, now I got to do this math here. So 50d 100 over c is the 2 I already included, actually. Included that twice there. So I've got c times 100 over d times 2. So cross multiply and you'll get 50 times d over c over here. And then this one becomes just 2c and d. Well, so far I just got rid of the hundreds. I didn't really do anything else. And then at this point I think I can probably cross multiply. Yeah, 50d squared is 2c squared. And then therefore, if I isolate for c, I get c squared is equal to 25d, and therefore c is equal to 5d, like that. Okay, so c is equal to 5d right here, but this c is also equal to 20b. So 5d, instead of c, I'll put 20b, or 20 over b. Right, it was 20 over b, correct. So this case basically gives me d is equal to 4 over b. So d is equal to 4 over b. Put that in there. And I think that's it. That's about as far as I can go. Let's see, is everything in terms of one variable? Almost. We just have to get f and g in terms of b. And we can do that. That's not a problem. So I'll just do it up here. I want to keep the square here. So let's see. F is equal to 100 over d, right? But d we know right here is 4 over b. So we got 4 over b. Invert and multiply, and we get 100 over 1 is b over 4. And therefore that's 25 over 25b. So 25b. All right, we are almost done. We just have to get g. G is 100 over c. We want that in terms of b. So c is basically, I think we got it a little bit earlier. Right here we had c is 20 over b. Yeah, it's right here actually. So c is 20 over b, and therefore this looks like it basically becomes 5b. So I'll put 5b in there. And now do we have everything in terms of b? I believe so. We just have to figure out e. E is the only one we don't have. Okay, that shouldn't be a problem. We can just use this comparison, this row with this diagonal. So we got 50 times b times c, which is 20 over b, is equal to 50 times e times 2. On this side the b's cancel and I get 1,000, and this is just 50 times e times 2. And solving for e, you get 10. Ooh, we get a number for that. Okay. All right, now we are done. So now we can finally figure out the value for the possible values of g. Okay. So therefore, concentrate on this guy right here. Since d is equal to 4 over b, and d and b are both integers, the only way that you can get an integer for d is if b is either 1, 2, or 4, correct? Because 4 divided by b has to be an integer, and that's the only way. So these are the only possible values for b in terms of positive integers. And then look at g. G is what we're interested in, and G is equal to 5b. So the corresponding values for G, if b is 1, 2, or 4, would be 5, 5 times 2, 10, and 5 times 4, which is 20. So these are the only possible values for G. So the sum of all the possible values is 5 plus 10 plus 20, which is 35. And therefore, after all that, we get 35 for number 22, and therefore the answer is C. Polynomial x to the power 3 minus 2004 x squared plus mx plus n has integer coefficients and 3 distinct positive zeros. Exactly one of these is an integer, and it is the sum of the other two. How many values of n are possible? So we've got 1 times x to the power 3 minus 2004 x squared plus m times x plus n. And it has 3 roots, or 3 zeros, and I'll just call them a, b, and c, the 3 roots. And they tell you that 1 is an integer, so I'll let this guy be the integer. And the other two obviously are not integers. So there's some number. I don't know what they are. But they give you an important clue that not only is the first guy an integer, but it is the sum of the other two. So it equals basically b plus c. So those are our roots, b plus c, b, and c, of that form. Okay, and lots of different approaches to this question, really. I mean, it can go in one of many ways, but I'll try to do it in what I think is the best way to explain. So if these are my roots, that basically means that if I were to factor this guy, I would be able to factor it in the following way. X minus a, x minus b, x minus c is equal to this big long thing, x to the power 3 minus 2004 x squared plus mx plus n. Right? I hope you agree with me. Now, does that help us at all? Well, I don't know. We'll see. But one thing is for sure, that you definitely need to remind yourself of those rules, because they're going to come in handy. The rules that quickly allow you to calculate the sum of the roots and the product of the roots. If you have a polynomial of this form, the sum of the roots, I hope you know this, is minus b over a. Okay? And the product of the roots will be equal to minus d over a. Okay? Why minus d over a? Because this is an odd degree polynomial. It has x to the third as its first term. If it was an even degree, it would be positive d over a. Okay? So that will definitely come in handy in this question. So let's see if we can initially use that. Let's try this guy right here, sum of the roots. Sum of the roots, well, what are my roots first of all? They're a plus b plus c. That's the sum of the roots. And we know from our little formula here that that's minus b over a. But be careful, don't just put minus b over a. That's not going to help you. It's minus b over a in comparison to the polynomial. So what is my b in this case? It's minus 2004. So it's minus 2004. And then my a in this case is a 1. I purposely put that 1 there to let you know that is the coefficient. So that means that a plus b plus c is just 2004. All right, the sum of those roots. Now a, we are told in the question that it's b plus c. So I put that in there, b plus c plus b plus c is equal to 2004. And this just becomes 2b plus 2c is 2004. And factor out a 2 and get b plus c is equal to 1002. All right? So a little bit of progress, I think, so far. But what's interesting is that b plus c is right there. It's one of the roots. So we just got one of the roots. It's the numerical value of that root, 1002. So I go back up here, and initially I wasn't too convinced that, I don't know if that helps me, but it helps me now. I can put that root. Instead of x minus a, I can put x minus 1002. Now, b and c I don't know. I don't know their values. So I'll just leave them as b and c. All right? And then, of course, I got to write out the full equation of that polynomial. All right, so I hope so far you're following. There's no magic. There's no tricks so far. And hopefully there won't be any real tricks. Now, at this point, I get to a point where I kind of think, well, I just don't know where to proceed now. Okay, so far I've done everything I can. What do I do? Well, concentrate on this guy right here, okay? If I were to multiply that out, it's basically a quadratic, right? And a quadratic is always of the form x squared minus dx plus e. You know, it's always sort of like that, right? And then this one, of course, it's the same thing. Now, if you concentrate on this right here, we should be able to get a little bit more progress. How? Using the same formulas up here. That's why those formulas are so important. Now this I wrote to represent this, correct? So let me ask you, what are the roots of this guy? Well, it's b and c. That's why it's factored that way. So since I wrote this to represent that guy, the roots of this are also b and c. Okay? And that's going to make a little bit more sense as I move on. All right, think, okay, fine, no problem. Okay, whatever. So how does that help me? Well, then look at this guy right here. Sum of the roots. Sum of the roots of this guy. Well, using this formula minus b over a, the sum of the roots will be minus b over a. So I've got minus d over a, which in this case is 1. And then we know the roots are b and c, so that equals b plus c. So that means d, my big D, is equal to b plus c. So you see how I got that there? Right? But b plus c, we know, is 1002. So there you go. I just got a numerical value for d. So that helps, right? So now I can go back and I put that in there. X minus 1002, x squared minus 1002, x plus e is equal to x to the power of 3 minus 2004, x squared plus mx plus n. All right, at this point you probably forgot what the question is even asking. That's what happens sometimes with these long questions. They're asking how many values of n are possible. Okay, what's n? Well, n is our last digit right there. Okay, how many possible values of n? How do I do that? Well, you do that by figuring out how many possible values of e are there. And once you get that, that will basically be how many possible values of n. Because e basically, if you multiply this whole thing out, 1002 e basically represents n at the very end. So if we get the number of values of e, n basically is the same. Okay? So here we go. So we have to concentrate on this guy right here. Okay? Now, this guy that I just circled in red has roots, and we know those roots are b and c, because we basically wrote that to represent this. And then we also know that b and c are not integers, correct? Because b and c were roots, and only a was an integer, and b and c therefore were not integers. So that means that this equation, which is a quadratic, has solutions that are not integers, namely b and c. All right, no problem. Let's figure this out. How do we find the solutions to a quadratic equation? Well, you definitely know that. You set it equal to 0 and use the quadratic formula. So minus b minus 1002 plus or minus the square root of b squared minus 1002 squared minus 4ac all over 2a, like that. And this basically becomes 1002, but I'm going to divide through by the 2 there, so I get 501 plus or minus. This will become, if you were to keep it in 1002 and divide by 2, it would become 501 squared, and then bring out the 4, and then that would divide by 2, so this becomes e, like that. Now this gives us two possible real solutions, right? One will be plus and one will be minus. But that only happens when there's a certain range for e. First and foremost, this discriminant has to be greater than 0, and that discriminant is 501 squared minus e. If it was equal to 0, we would only get one solution, and if it was less than 0, we would get basically an imaginary. So this condition is true if you want real solutions. And then the other solution has to be positive, right? The other condition, because not only are they real, they're also positive. So that means that this discriminant also has to be less than this guy here, 501 squared. Because if it was greater than that, it will give a negative answer. So this condition is true right here to give positive solutions. Okay, so this condition is for real, and that condition is for positive solutions. So that basically means that for the first guy, let's just concentrate on the first guy. 0 is less than 501 squared minus e. So therefore, looks like e is less than 501 squared. 501 squared is 251,001. All right, so all the numbers that are below 251,001. Okay, but we also got to take into consideration this one, which states that 501 squared minus e is less than 501 squared. If you do that, we basically get that e is greater than 0. Okay, so therefore our range for e is it's greater than 0 and it's less than 251,001. But there's one final little thing that a lot of people would miss, is that, remember, these solutions cannot be integers. So this guy right here will become an integer sometimes. We've got to subtract those ones. When does it become an integer? For any value of e that makes this a perfect square. So if e was, for example, 0, e can't be 0, but if it was, it would be 501 squared, taking the square root. You see how that becomes an integer? Or any value of e that makes this 500 squared, any value of e that makes that 499 squared, those will give integer values, and you can't have those. So from this list, we have to subtract all the values of e that would give integer solutions, and there's 500 of those, because 500 times this can be a perfect square, right? We got 500, 499, 498, all the way down to 1. So in the end, here we basically had 251,000, right? Because less than that. So we take 251,000 and subtract from them the 500 values of e that would give integer solutions, and that gives you a total of 500. And remember, these are the values of e, but we earlier said that e has a relationship with n where n is just 1002 times e. So this not only represents the number of values of e, it also represents the number of values of n. So since n is equal to 1002 times e, the same amount of integer values of n are possible. And that amount is 250,500. So going back to the beginning, we've got 23, 250,500 is C. In triangle ABC, AB is equal to BC and BD is an altitude. Point E is on the extension of AC such that BE is equal to 10. The values of tan CBE, tan DBE, and tan ABE form a geometric progression, and the values of cotangent DBE, cotangent CBE, cotangent DBC form an arithmetic progression. What is the area of ABC? So first, let's label what we can. Let's make this as helpful as we can. Angle DBE, I will label as X. And angle DBC, I will label as Y. And therefore, if I put that in my diagram, angle CBE will be X minus Y. And angle ABE will be X plus Y. So this is Y. This is Y. Correct? Because AB is equal to BC. That is an isosceles triangle. And this in here, I gotta squeeze that in there, is X minus Y. Okay? Now let's go with the information they tell us in the question. They tell us that the tan of CBE, which is X minus Y in my labeling, the tan of DBE, which is the tan of X, and the tan of ABE, which is the tan of X plus Y. These three form an geometric progression. Okay. Geometric progressions are of the form A, AR, AR squared, right? So that is helpful because if you take any two, like if you take AR and divide it by A, it gives you R. And if you take AR squared and divide it by AR, it becomes R. So that can help us. So let's do that and see what we get. So the first one right here, AR over A, basically means the tan of X over the tan of X minus Y, like that. And that's equal to R. But we can get R in terms of a ratio of those two terms, which would be tan of X plus Y all over the tan of X, right? Now, just in case you forgot the tan rules, I'll just list them on the side here. Tan of A plus B, this will be a little bit of a refresher. It's the tan of A plus the tan of B all over 1 minus tan A times the tan of B. Okay? And the tan of A minus B was or is tan of A minus the tan of B all over 1 plus the tan of A tan of B, like that. Okay? So let's use those tan rules and proceed with our question. First, let's cross multiply. I think that will help. So that becomes the tan of X all squared. And now we get the tan of X plus Y. And multiplying that by the tan of X minus Y. Okay? So let's proceed with this using our tan rules. So this will be the tan of X all squared tan of x plus y. So we got tan of x plus the tan of y all over 1 minus tan of x, tan of y. And then this guy becomes the tan of x minus the tan of y. Got to make sure I don't copy my own handwriting wrong. Plus the tan of x times the tan of y. All right. And I guess at this point we just have to do the algebra. There's no shortcut, unfortunately. If there is, please let me know. So this becomes the tan of x squared. Well, the good news is a couple of things cancel out here. So you got tan of y squared. Yeah, plus or minus. Okay, that's good. And then I think the same kind of cancellation happens on the bottom. You have 1, that cancels the middle two terms, and then you just get minus tan of x squared, tan of y squared, like that. Okay, good. So at this point, I think, let's see, we cross multiply most likely. So that gives you the tan of x squared minus the tan of x to the power of 4 times tan of y squared. And that is equal to the tan of x squared minus the tan of y all squared. Tan of x squareds go, these guys here. And then we can put everything on one side, I think. And we will get the tan of x to the 4th, like that. Tan of y squared minus the tan of y all squared. Factor out now. You can factor out the tan of y squared. And if you do, you'll just get left with the tan of x to the power of 4 minus 1. All right, great. So that means the tan of y is equal to 0, but that's not possible because you can't have a tan of y equal to 0. So the only possible solution is tan of x to the 4th is equal to 1, and therefore the tan of x is equal to 1, and that means x is 45 degrees. All right, so we took care of our first piece of information. So now let's go back to the original question and look at the next piece of information, cotangent. All right, so they're saying that the cotangent of DBE, CBE, and DBC form an arithmetic progression. All right, so let's do that on the side here. Probably keep our tan rules. We might need them. We might not, but let's see. So they're saying that the cotangent of x, cotangent of x minus y, and the cotangent of y form an arithmetic progression. So it's like a plus d, a plus 2d, like that. And let me just double check I got my angles right. DBE, which was x. Okay, that's x. CBE, which is x minus y. Got that one. And DBC, which was y. And I got that one. Okay, good. I got my angles right because I don't want to make that mistake. Okay? Now the fact that they form this arithmetic progression again helps us, right? Because if you take the second term and subtract from it the first term, like a plus d minus a, you just get d. And in a very similar way, if you take the third term and subtract from it the second term, you get a plus 2d minus a minus d, and this is also d. So since those are equal, we can set them equal to each other. So let's do that. Let's take the second term, which is the cotangent of x minus y, and subtract from it the first term, cotangent of x, and that's basically equal to d. And we can get d in the same way by subtracting the third term and the second term. So that basically means cotangent of y minus the cotangent of x minus y. All right, just like that. Let's see what we get here. Well, the good news is we got a value for x, right? One of our variables, we got it. All that hard work should be, helpful in some way. It should be useful. X equals 45. The fruits of our labor label should be utilized in some way. So the cotangent of 45 minus y, put that in there, minus the cotangent of 45. Hopefully this will help us. And let's see here. Y I don't know, so I can't put that in. And then I put cotangent of 45 minus y. Okay, I think we can collect like terms here. I think this is the same as that, so put it on one side. 2 times the cotangent of 45 minus y. And I put everything on this side here, cotangent of y plus the cotangent of 45. Okay, cotangent of 45, well, I'm certain that you know that the cotangent of x is equal to 1 over the tan of x. I hope it is. And therefore, the cotangent of 45, and even if you don't have a calculator, is 1 over tan of 45. The tan of 45, even if you didn't know that, it's 1. But of course you did know that. So that means that cotangent of 45 is 1 over 1, and which is of course just equal to 1. So we can plug that in there. And let's see here, that gives me 2 times the cotangent of 45 minus y is equal to the cotangent of y plus 1. All right. Now at this point, I'm going to convert them all to tangents. I don't want to work with cotangents. Why memorize additional formulas when you can just convert it in a very simple way by flipping it to tangent like that? 1 over 10. Simple. There's no reason to memorize. It's bad enough I've got to memorize these guys over here, right? So that's why I kept them in the photo or the frame, because this is 45 minus y, so I've got to use this guy right here. So using our tangent rule, we'll get 2 over the tan of 45 minus the tan of y, all over 1 plus the tan of 45 times the tan of y. And this is just 1 over tan y, and I'll just get a common denominator while I'm writing this out, tan of y over the tan of y. Okay. Now the tan of y we know is basically the tan of 45, which is 1. So I'll keep that in the equation. So I got 1 minus the tan of y over 1 plus 1 times the tan of y. All right. So this just becomes 1 plus tan y over tan y, like that. This over here, invert and multiply, so you get tan 1 plus tan of y. And don't forget that 2 there. And that is going to be over 1 minus tan y, like that. 1 plus tan of y over the tan of y. All right. Cross multiply this guy. So we get 1 minus the tan of y all squared. Cross multiply that guy. Be careful here. 2 tan of y. And we get plus 2 tan of y squared. All right, things are starting to look pretty good here, I think. We can now put everything on one side. And if we do, we'll get 3 tan of y all squared plus 2 tan of y minus 1. And I do believe this factors. Let's see here. 3 tan of y, 1 and 1. But let's see, negative, positive, right? 3 minus 2, right? Or 3 minus 1, actually. So that means that the tan of y is either 1/3 or negative 1. Okay. Now this negative 1 we are not going to use because we're dealing with lengths of a triangle shape. So I'm going to use tan of y is equal to 1/3 because I can't have a negative length. All right. All that hard work to get the tan of y is 1/3. All right. Let's go back to our original question now that we've done all that. What is our original question asking us? Well, before we forget, let's put in what we found out with all our hard work. Found out that x was 45 degrees, and we found out that the tan of y was 1/3, okay? They want us to figure out the area of ABC. ABC. So this one right here, ABC, this triangle. Okay? Well, the area of a triangle is 1/2 base times height. The base is right here, AC. Now, I don't know that, so I'll just label it. I'll label DC is equal to A, like that, and then AD is equal to A, because remember, BD, they tell you, is an altitude. And because it's an isosceles triangle, it will cut that in half. So I got 2A in there. And then 1/2 base times height, the height is BD. And I'll just put it as BD. That's fine. Okay, so now where do I go here? Well, I've got to utilize this. The tan of y is equal to 1/3. Now, what is the tan of y? The tan of y, if you look at this triangle right here, that one right there, it's opposite over adjacent, right? So that means opposite, which is A, over adjacent, which is BD, is equal to 1/3. Correct? So that basically means that 3A is equal to BD. So I can go back here and put in that in there. So this is, if you simplify, just becomes A times BD. And if you want to put everything in terms of BD, I think that's perfectly reasonable. So instead of A's and BD's, we'll just put A is equal to what? BD over 3. So we'll just put that in there. BD over 3. So this becomes BD squared all over 3. Okay, if we can find BD, we are set. What is BD? It's the altitude from there to there. Okay, no problem. We should be able to do this. And we'll be able to do that with this triangle right here. BD all the way till E, that triangle right there. All right? Now in triangle BDE, this angle right here, that is angle DBE, is equal to, right here, x. And we know that x is equal to 45 degrees, which is 45. So we can use trigonometry once again, and this time I'm going to use cos. The cos of 45 is equal to adjacent, which is our BD, over our hypotenuse, which is BE. And at this point, you probably forgot that they even gave you this. They tell you that BE is 10. So BD is equal to, over 10 is equal to cos of 45. And the cos of 45 is one of those angles that, you know, most people know just by inspection. You don't need a calculator. And it is 1 over root 2. 1 over root 2 is BD over 10. So therefore, BD is equal to 10 over root 2. So perfect. Now we can go back, substitute that in. We've got 10 over root 2 all squared over 3, and that looks like 100 over 2 times 1 over 3, and that looks like we got 50 over 3. And there you go. 50 over 3 in this long, exhausting question. So the answer is B for number 24. Given that 2 to the power of 2004 is a 604-digit number whose first digit is 1, how many elements of the set 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, all the way to 2 to the power of 2003 have a first digit of 4? So what I'm going to do is I'm going to make a list and see if there's any kind of a pattern. So I've got 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. And for each, I will write the first digit. So here is the list here. I've written out till 2 to the power of 19. And you'll see a little bit of a pattern here. 1, 2, 4, 8, and then 1, 3, 6, and then 1, 2, 5, and then 1, 2, 4, 8, 1, 3, 6, and then 1, 2, 5. And you think, oh, okay, no problem. I've got this all figured out. And that's what I thought too. But then I said, well, it's number 25 on AMC 12. So the hardest, well, not necessarily the hardest question, but definitely one of the hardest questions on the senior level math contest. It cannot possibly be this straightforward. And it isn't. Why? Why isn't it this straightforward? What's the story here? And I'll tell you, because it looks like it follows this pattern, right? And it does for the first 2 to the power of 19. But eventually what happens is something very unfortunate. And that is that this guy, 1, 2, 4, 8, it changes. It becomes 1, 2, 4, 9. And that happens because one of the numbers becomes so large, it becomes whatever, like 4, I don't even remember, but 4.5 million or what, something like that. And then when you double it, it becomes a number that starts with the digit 9. And that is the problem. That is the thing that makes this question so challenging. The good news is that the pattern does continue, but you've got this little change here. To make matters worse, this pattern also changes eventually. Initially it's 1, 3, 6, 1, 3, 6, right? But eventually it becomes 1, 3, 7. For the same reason, that eventually the numbers become big, and then when you double it, it becomes 7 as the first digit. All right, well, how do you approach this then? Okay, try to explain this as carefully as I can. So look at first those 4. You got 4 of them, right? There's 4 numbers in a pattern. The next one is 3 numbers in a pattern. The next one is 3, and then 4, and then 3, and then 3 like that. Okay? So that's pretty straightforward right there. So before I start explaining this whole big subset here, let me just explain it for this subset until 2 to the power of 19. Okay? And then I'll extrapolate till 2 to the power of 2003. Okay, so let's just look at these guys. So let's move this question up. Let's concentrate on what we have on the screen. Okay, we've got 2 to the power of 0 until 2 to the power of 19, correct? So we've got how many terms? We've got 20 terms. All right. Now, how many little subsets do I have? I got 1 here, 1 here, 1 here, 1 here, here, and here. I've got 6 of them, right? Okay, great. 6 of those little subsets. But I'm going to break them up into subsets of 4 and subsets of 3. Okay? So how many subsets of 4 do I have? I've got 2 of those guys. This one and this one. And each of them has 4 numbers in it. Okay? Then how many subsets of 3? I've got these 4 groups. So I've got 4 of them. And each of them has how many numbers? Has 3. And if you total it all up, it should equal 20, and it does. 2 times 4 is 8. 8 plus 12 is 20. Okay, so 20 tells me how many terms or how many powers of 2. And we indeed have 20 of them, right? 2000 until 2019. So I hope you understood how this equation was calculated. All right? Now, one more thing is that when you look at these numbers, right, I want you to make a list of the numbers at the end of each subset. So this guy, for example, is 8. Correct? So that number is already there. This, 2 to the power of 6, I want you to write that number out. It's 64. 2 to the power of 9 is 512. Just the ones at the end of the subset, and then I'll explain what I mean. 2 to the power of, let's match this up, it was 2 to the power of 13. And that's 8192. 2 to the power of 16 right here, 65536. And the last one, 2 to the power of 19, 524288. Now, why? What's the point here? Why do I need those? Well, now I want you to count the number of digits in each of those numbers. Well, in 8, there's only 1 digit. So I'll write that here, number of digits. And this will become clear once I finish. Number of digits in 64, well, there's 2. Number of digits in 512, 3. Number of digits in 8192, 4. Number of digits in 65, 536 is 5. And the number of digits in 524288 is 6. Do you see a pattern there? 1, 2, 3, 4, 5, 6. Correct? So in this mathematical formula, if we get to the end there, that final number, in our case, has 6 digits, and that must equal this number plus this number. And it does. So that is the key to this question. It's a tough question. Now, I'm not going to brush this off and say, oh, you can do this. This is tough. It's not easy. So what I have to do is I have to come up with a formula. And I can do that. Basically, I'm going to let this be x, right? If I'm extrapolating all the way till 2000, or 2 to the power of 2003, right? Yeah. And I'm going to let this one be y. So in a very similar way, it'll be x times 4 plus y times 3. And it's not 20 this time. It's how many? 2004. Why? Because in our set, we have 2 to the power of 0 all the way to 2 to the power of 2003. And that's 2004 numbers. Okay? So I'm following basically this formula up here. I'm just extrapolating it to 2004 because that's how far they want us to go for powers of 2. Okay, and then we also figured out this little neat formula that x plus y is equal to the digits in the very last one. Okay, now do we know that? Well, here we know it's 6, but what's the number of digits in the very last one? They tell you in the question. Well, they tell you some of it. 2 to the power of 2004 is a 604-digit number. Okay? All right. Well, geez, does that help me? I mean, I want to know how many digits are in 2 to the power of 2003. All right. Well, how do I work with that? Well, 2 to the power of 2004 is 1 after 2 to the power of 2003, right? Now they tell you a little bit of information about 2 to the power of 2004. It has 604 digits and the first digit is 1. So we've got 604 digits, right? Number of digits. And first number, first digit. Now we need to figure out the same information for 2003. Well, for 2 to the power of 2003, I don't know. I have no idea what is the first digit. But the good news is that this is a 1. And therefore, because it's a 1, this basically means that it's the start of another subset. You notice the start of any subset is always 1. Did you notice that right there? So 2 to the power of 2003 is 1 before it. So if it's 1 before it, its first digit could be 8, its first digit could be 6, its first digit could be 5, right? So we don't know, so I'm going to put a question mark there. And that's okay, we don't need to know, but we definitely need to know the number of digits. If the number of digits is 604 for 2 to the power of 2004, 2 to the power of 2003 will have how many digits? Well, remember, let's look at this one here. This subset, these guys had 6 digits, right? For their numbers. The next subset before it, the number had 5 digits. So it's 1 less. So this has 603 digits. Okay? So I wanted to take that slow there. 2 to the power of 2003 has 603 digits. All right, let's go back to our formula. X plus y equals the number of digits in the very last term. 2 to the power of 2003, we just figured out, has 603 digits. Okay, so that is our system of equations, this one and this one. If we solve this, we will get values for x and y. Now, okay, well, how does that help us? X represents what? It represents the number of times that 4 will appear as the first digit. Right? Let's go back and take a look at that a little bit. X in our little formula here was 2. Correct? How many times did 4 appear as the first digit? Once here, once here. 2. Everywhere else, there's no 4. You see how that works? So x represents the number of times that 4 will appear as the first digit. So note, x represents the number of times that 4 appears as the first digit, and that is what they are asking in the question. So let's use these two equations to solve for x and y. So from this guy here, we basically get that y is equal to 603 minus x. And we can substitute that into here, and we will get 4x plus 3y is equal to 2004. 4x plus 3 times 603 minus x is 2004. So 4x plus 1809 minus 3x is 2004. So this looks like x, and this is 2004 minus 1809, which is equal to 195, like that. So there you have it. And since x represents the number of times that 4 appears as the first digit, 4 appears as the first digit 195 times for the set that goes all the way up to 2 to the power of 2003. And therefore, number 25, the answer is B.